Okay, good afternoon, Year 12. This is the second chapter, which is Module 3. So it's the start of Module 3. It is the first of the proper topics, shall we say. So all the stuff before this is going to appear in every single part of the course. The ideas of forces, vectors, and so on. So Module 3 is all about motion and static forces. So this is the first bit. This chapter and the next one, and to be honest, the vectors are very much kind of the architectural type of stuff. It's the properties of matter, it's the way they're balanced, it's the way everything holds together. So we're going to start with practical for the Hooke's law, bring that in because that takes us into materials. But before we do that for today, what I'm going to do is actually just do a little bit on background ideas. Okay, and bring some in. So looking at physical properties of matter or mechanical properties. So you've done little bits before. Our big idea is really bringing this idea of the mathematics of materials in terms of their strength and so on. But that's of materials, not of springs. Okay, so we'll start with springs. So basically, simple ideas at the beginning. I know a lot of this, so these are quite short and factual. The best thing is to actually look at the PowerPoint and it will take you through with a little bit more depth. So, density, we know roughly what that is. That's about particles within the volume. If you take bread, for example, white bread, and you throw it onto water, it's less dense, so it floats. If you throw it on after you've folded it in half and squashed it down, it will sink. And the more times you fold it, the more times you squash it down into the same thickness, you'll find that, of course, you're packing the molecules closer and closer together and you're changing its density. So, just pick up, because again, warning, through a lot of this stuff, chemistry is obviously about materials as well. We are using the SI unit, so it's kilograms per meter cubed, not grams, not centimeter cubed. Okay, so these are big numbers. Around about 1,000 times higher than you get in chemistry. So, quick heads up, density, symbol rho, not unfortunately the only thing that has that symbol, but we'll work on it. And what you have is simply the equation rho is the mass over volume. Okay, so rho equals m over v. So, well, we use that quite a lot, and the density itself changes quite a lot depending on how things are. Obviously, it will depend on the mass of the molecules and how many molecules you've got. But you'll also find that man-made synthetic materials are fairly regular, but normal stuff every day, wherever you get it from, whether it's the ground, whether it's natural from trees and so on. They're going to range in density and you'll get fluctuations as well. Impurities or just higher density material. And so a lot of our work is kind of linking these ideas, but actually sometimes you need to go into more depth, like if we've got brass, well, it's made of two different materials, 70% volume. What's the density of that material? So copper, for example, and therefore how much does it make up in terms of particles? So there's lots of stuff like that that links in upper sixth when we start doing deeper into gas properties. But this is just a general idea. So I'm going to pick up on a couple of things. So static pressure, there's actually three types of pressure. But we're going to just look at the kind of the ones that are sat still. The simplest one in which most of them are based on is thinking about pressure underneath a surface. As it says here, in an area of contact. So in this case you get the classic F over A, force over cross-sectional area, area of contact. Okay, and so again, if we use proper units, newtons and meters squared, then what we'll get is something called pascals, and you'll see that quite a lot in this chapter. So pascals is a more convenient unit. Something's gone very odd here. This should be large m. There we go. So to the -3. per meter cubed. So that we're going to link into this. Hydrostatic pressure is where we're moving away from solids and thinking about liquids. We have, for example, gravity dams, which are dams that are just held in place by their weight, and literally they have to be thicker at the bottom because there's more pressure at the bottom. So anytime you've been up in an aircraft, you'll have experienced this. Ears popping as the pressure drops as you get higher up. Why? Because effectively we are swimming around in the bottom of the ocean. It's just the ocean is made of air. If you swim down into water, because it's more dense, the pressure builds up much more quickly. How do we know that? Well, there is an equation that summarises it. So this static pressure, or depth of water, depth of liquid type pressure, known as hydrostatic pressure, it comes from the equation that says H rho G. Okay, so it's the height of fluid above you, it's the density, and it is the effect of gravity. How do we get this? Well, it's not actually a hard step, it doesn't take a genius. If we go from our basic definition of what pressure is, force over area, then we know for this the pressure is higher at the bottom because there is all the weight of the liquid above. So we need the total mass of liquid above us and multiplied by gravity, and if we divide that by area, that's the same equation. Now this does assume that the pressure equation assumes that the density is all the same all the way down. Okay, so somehow we need to link that because we don't really know about the mass. It's the total mass of water depends on how much water is in the reservoir, the area of the whole reservoir, but actually this just varies with a narrow column, so it's the weight of water above. If we break it in, we know from above that mass over volume equals density, so m equals rho v. So what I can do is substitute that into the top here, so we have pressure equals, let's just do rho, sounds a bit better if you put the g first, but rho gv, and it's divided by area. Well, if we want the volume of the liquid here, then we just simply need the height of water and the cross-sectional area. So again, area here is important, but that height, that will give us the whole area. So rho g height times area divided by area, which of course cancels out, and so we end up with P equals rho g h. Okay, so quite a simple derivation in terms of what it is, and that's because it comes from this idea of, well, where's this weight, where's this force from, and it's the weight of all the water literally pushing against it. So simple derivations, some we do this year are more complex, but as long as we know the idea of why it happens, it's quite easy to put them together. Now, this does link in with one other complicated bit, and again, going to do this quite factually. We'll need to go into more depth next year. But it leads us into this idea of Archimedes' principle and the thing mentioned at the end of the last topic, which is upthrust. Okay, so upthrust is the floating force here that makes things float. Even if it's not floating, things are upthrusted because they're surrounded by a fluid. And in your case it's the air, if you're in water it's the water that should be there has been pushed out of the way. So what we've got here is, because of the actual small weight, let's say a little arrow down, we have a little arrow up, and those are equal size, they're balanced. Why? Because they add up to 0. That's not moving, the forces are in equilibrium. Well, if you've got an elephant stood on it, it's still floating, much bigger, but this responding force, this upthrust, is much bigger too. Okay, so it's always going to be equal to the weight of whatever it is if it is floating in equilibrium. If this was floating there, but when the elephant stood on it, it was on the bottom, well, you've still got the upthrust, but part of that upwards force will be also the normal contact force. Okay, so it'll still be total up equals total down. So let's just nip in and link that into a more useful way just to round it up. What that gives us is all kinds of different principles, and again the PowerPoint gives us in much more depth. But you can link the things together because we need to think about those forces in my little diagram there. And those forces have come from the pressure, and it's all to do with different densities of liquid, different depths of water or depths of fluid. Because of that we get different pressures. So if we want the force down at the top surface, then what we've got is pressure times area. Okay, so again it's due to that pressure, and we know that that comes from H rho G times by A. Okay, but this is literally the H there, whereas the upwards force is H plus D. It's that total depth of liquid to get to the bottom. We can ignore the ones on the side just to make it convenient. So if we're looking at the force on the bottom, the upwards force, then HGA, what we've got is that if we want the difference between them, then we just have to find out, the upthrust will be the difference between those two forces. So if you subtract them, that's our total upwards force, that's our total downwards force. If we subtract the difference between them, then we're going to have that, which is bigger, subtract that one, and we end up with D rho G A. Okay, so that's upwards versus subtract downwards. Okay, just put those in brackets. And what we can get from that is a distance there. That is the area of the bottom. So actually that's a volume. So that equals HGV, where V is a volume of object, and to be precise, because this is totally submerged but some aren't, so it's the volume of the object submerged. If it's only half submerged, then it's the bit of the object that's submerged. It's that bit there that's important. So what is that? Well, we've got the density, and the density up here is actually the density of the liquid, so let's just make that clear in there. That's our density. So actually none of this depends on the object itself apart from the volume. So what we've got is, if we put those together, density times volume equals mass, and because we've still got G, that's mg, and that is the weight of the fluid. Okay, so it's the weight of the fluid that is no longer there. So if you've got an object that's a meter cubed, there's a meter cubed of the liquid that's gone missing, that's been pushed out of the way, and it's the weight of that that is displaced, which is equal to our upthrust. Okay, which is a beautiful little idea, in that if we find out how much is missing, that's how much force is pushing up. So if we go back to here, we've got a little bit of volume missing. Okay, so there's our volume there. So there's a little bit of upthrust. Here we've got much more water that is being pushed out of the way, much bigger volume of water, and so there's a much bigger upthrust. Okay, so that's how it all works, and it doesn't matter how much is submerged, you're going to get that. Obviously, if that's totally submerged, you've got the maximum upthrust. Okay, it doesn't get bigger just because it's further down in the water, assuming that we have this constant density lower down. Okay, so few ideas thrown in. They're going to feature every now and then, again just a little bit randomly, so we're going to be talking about density all over the time. If we're talking about density it's really the way to find the mass or the volume. So that'll be the things that are needed in your equation, that'll be needed in your calculation, but you'll be given the density of the material. So from the density, that's your hint to go, I'll need the mass. The only case that isn't true is if you're just walking about how much pressure there is as you swim down inside a liquid or a gas, both of those fluids. So there you actually need the density, but everything else, conveniently, mass is usually the thing found from density. We've got weight, so that can be pressure underneath something, it can be the pressure down in something, and again, to sum it up, it can be the pressure difference which causes the upthrust. So it all links nicely together. That density is needed to make that happen. If we had something that is more dense, there is a bigger upthrust, you float better. If anyone's seen any pictures of the Dead Sea, it's incredibly salty, so it's much higher density, and therefore people float on the surface rather than half submerged in the surface. Okay, and a little mention of balloons, which is again, exam boards love balloons, so let's just put hint for exam questions. Okay, thanks very much guys, we'll leave it at that.